I'll blame that on me rather than you.
Definitely you. That's the right one.
That's the right one. There you go.
So what's more, you don't get a picture of me, so that's good.
Just before I forget, so speakers, I will leave the microphone available if you would like to use it. But if you're happy projecting, don't feel you need to. There you go.
Thank you.
No worries. Enjoy.
Thank you. Morning, everyone. Morning. That's good. You're awake. I'm Mark Burstow. Currently Network Rail, Principal Vehicle Track Dynamics Engineer. Brilliant job title. Longest job title in the history of the railway, I think. I'm the only one in existence, which is both a blessing and a curse, really. A bit about me. I was a graduate of this university, and then a postgraduate of this university, and then I did 9 years as a postdoc at this university. So whereas Steve said yesterday that 6 years was too long in academia, I would argue that is not the case. I was 9 years, and it was a long time for where I've ended up now, but actually I think it was really good. It taught me a lot of things, and I think if I'd have gone into the rail industry earlier, I probably wouldn't be in the position that I am now because of all that learning that I achieved while I was doing academic research. So, you know, we all carve our own research paths, our own careers, and I don't think there's a right way or a wrong way to do it. But certainly for me, I've enjoyed my academic career, and I've also, well, I am still thoroughly enjoying my career in the rail industry itself. So I left academia, 9 years research into fracture mechanics, which served me in very good stead for what I walked into when I joined the rail industry. And when I joined the rail industry, I started working a consultancy. So doing consultancy work, pretty much using fracture mechanics. That was why I was employed for my experience in that. Carved out a bit of a niche for myself in that area, which then allowed me to move from being just a fracture mechanics expert, but also turning into more of a vehicle track interaction specialist and understanding more about why we should be concerned about the impact of vehicles on the track. And so then that allowed me then to transition into Network Rail. 18 years ago, I made the move from consultancy into Network Rail. So that's me. What am I going to talk about? Well, I thought since I've been around a long time and I'm feeling really old, and one of the things that makes me feel really old is that when I look around this room, I see someone whose father I worked with on research into some of the things that I'm going to be talking about today. Thanks, Martin. So I thought it was always worth looking back to see where you've come from, to understand how you got to where you are, just to give yourself a bit of encouragement as to what you've learned and what there still is to learn and where you want to go. So what did we learn along the way? And Paul's not here today, is he? But yesterday he was talking in his keynote speech, he was talking about silo thinking in the rail industry. And I think a lot of the things that I'm going to talk about today, a lot of the things that we didn't get to grips with was because we were doing lots of silo thinking. And I think my role is very much to try and get out of that, because I'm, you know, as a vehicle track dynamics engineer, I'm trying to look at both sides of the wheel-rail interface. And I'm not just looking at the track and blaming the vehicles. And I'm not just looking at the vehicles and blaming the track. I'm actually trying to find out what's happening in the middle. And on top of that, we've also got the problems of control period 7. We've got less money, we've got less access to track, much less access to track than when I started on the railway. And it's how can we actually make the most of that? But we've also got much better data, which makes things easier. So let's go back. Time in history, rolling contact fatigue. Steve talked a bit about this yesterday. So rolling contact fatigue, basically surface defects in rails, had been an increasing problem for BR from the late 1960s, early 1970s. The graph down here is from some data that was accumulated or reported regularly by one of British Rail's metallurgists about reviewing the defects that we were getting in track and all sorts of other problems. But and this is just an extract from that. And so we can see how the number of defects that we were getting in rails was actually increasing significantly over a period of about 20 years from the early 1970s onwards. No one really understood where they came from. No one understood what caused them, other than clearly it was vehicles rolling along the track. But we were getting cracks in the rails, an increasing number. No one really knew what had changed. We were managing rails in pretty much the same way. Rail steel, there were some changes in rail steel. It was actually becoming cleaner. But nothing really that would point out to having a problem. But it was very much seen, silo thinking, it was very much seen as a metallurgical problem. So it was left to the material scientists and the metallurgists to understand what was causing it and to look at it. And then in October 2000, a train derailed at Hatfield in Hertfordshire, London King's Cross, the midday service from King's Cross to Leeds, derailed as a result of a rail break from rolling contact fatigue that occurred underneath the train as it was passing around a curve at Hatfield. Heart of privatisation, very much big divisions between wheel and rail. There were also lots of management problems because of the contractual arrangements, but largely the findings is that there was not a holistic view of the railway, and that the wheel and the rail interface was seen to be two completely separate. Well, the wheel side and the rail side were seen to be two completely different aspects, and they didn't talk to each other. And it always comes back to this famous quote from Sir Peter Parker, who was chairman of the BR board from 1976 to 1983, in that the railway always falls down at its interfaces. Think about it, it's true. So from then on, there was a lot more focus in rolling contact fatigue research. That's one of the reasons why I was able to leave academia and walk into a job with a consultancy, because we were doing research into this sort of area. Fracture mechanics expert, that's just what we need. We'll walk into this. And I spent a lot of time starting to get involved in these sort of cracks, looking out, walking out, taking photos, walking track in the days when access to track was much easier. So yeah, very often you're getting these surface initiated cracks, which then risk growing down through the head of the rail, like Steve was talking about yesterday. We've still got RCF, we've still got a lot of it. Back into silo thinking, we do a lot about managing RCF, but I don't think we do enough about prevention of it. So we've got lots of management techniques to monitor it. So we do a lot of rail grinding. Thanks, Lucas. Lots of rail grinding. I don't like rail grinding. I hate to disappoint you. I don't like it. When you see pictures like that, you think there's an awful lot of energy that's going to waste there, just removing material from the head of the rail for no purpose. Why? We do a lot of rail grinding to try and manage RCF. We do rail milling now. The picture on the top right is of a rail miller. So that actually takes off even more material off the head of the rail, but it leaves a lot better surface finish. And we've got lots of fancy data systems now for measuring RCF. So this is our eddy current system. Each of the lines, the horizontal lines along there, is for a different date. So brilliant, you think we can get RCF data in great detail. But look at it, they're all mileages along the bottom, but they're all offset from each other. So although the system is telling us where it is, it doesn't really know where it is, because I don't believe that the RCF is moving from point to point along the track. That's actually a measure of all the RCF at the same place. But if you try and line up any of these clusters, so if you line up all the blue ones there, you'll find that the green ones don't match. And if you line up the clusters on the green ones, you'll find that the blue ones don't match. So there isn't even a common distance datum for these measurements. But this is useful data if you want to manage RCF, bit harder to use it in a research project to try and see how things are changing. We are trying. So, going back in time, BR's interest in the RCF problem had really, or rail breaks, had really been looking at the Tascheval problem. So a Tascheval is an inclusion within the head of the rail from which a crack will grow, which is slightly different from the surface-initiated cracks, which in most RCF is these days. So when I started to get involved in this, 2001, RCF was relatively little understood. Modelling was dominated by the vertical forces being imposed on it. So there's a lot of focus on the contact stress between the wheel and the rail. There were lots of theories and laboratory studies, and I know there's people in this room who are actually involved in a lot of that, but there was a lot of modelling and laboratory studies, theories around as to what caused it, and they worked. There were pretty good theories, they worked in the laboratory, but they weren't able to explain the way that RCF actually appeared in the field, the way that cracks appeared in clusters on a piece of track. So you could go down a piece of track and you'd find on a straight piece of track there was a cluster of cracks here, then nothing, and a cluster over here, and then nothing, and a cluster over here. These theories weren't really able to explain that. So we really lacked the knowledge about what was actually being, well, the forces which were actually going into the rail and the mechanism, what was going on. So one of the first things that I was involved in this area was actually two areas of modelling. One was crack growth modelling. A lot of work had been done to determine crack growth rates in steels, and there was a lot of research that had been done here in Sheffield in the 1980s with Mike Brown, looking at crack growth rates and mixed mode crack growth rates, so how the crack growth rate changed as the angle of the crack changed within the steel. And that was able to produce graphs like you get at the top there, where you can predict how the crack is going to grow over time, which gave us one management method, which was you could work out how much material you needed to grind off the rail to actually curtail the crack. I think Steve mentioned that yesterday. But the real problem came back to cracks initiating. Isn't it better if we could actually stop them appearing in the first place rather than trying to manage them after we've got them? But the best that we could do with the data that was available was build a statistical model. So we had what was then classified as big data. You'd look at it now and you'd say this is very small data. But this was a database, call it a database, it was an Excel spreadsheet, which was compiled by track engineers across every rail track zone as it was at the time, who said exactly which curves had RCF and how severely RCF was on those curves. And we got hold of that database, and that was our first look at big data. And we spent a lot of time trying to analyze that data and see what it could tell us. The truth is, I'm always wary of big data because given the input parameters that we had and the theories available at the time, nothing actually fitted to explain why that data was the way it was. So the best that we could come up with was a probabilistic model like this. And if you look at the y-axis, that's 30%, okay? The best prediction that we can give is that a curve, in this case, somewhere around about 1,500 meters, has got a 30% chance of getting RCF. If you want to manage RCF, if you're an infrastructure manager, that's hopeless. That's like a stab in the dark, that is. But that was the best that we could do with the data we had available. One of the big things I learned from this is that big data is hopeless unless you've got all the influencing parameters, and then you can fit them to it and start to develop models. So the next step was then to say, actually, we do need to better understand the forces that are going into the wheel and rail. So we moved away from this big data, what we refer to as a macro approach, trying to fit fracture mechanics theories to the whole of the network, and said, let's just look at a very small part of the network and understand that and analyze that to death in very great detail. So we found a number of sections of track. Each was probably about, the one that this was taken from is like 500 meters of track, probably at most, and took a much more detailed approach. So effectively, we're looking at a much smaller set from that big data, but being able to get a lot more information about that small set and analyze that. So we went out, we did track surveys in the days when we could go out and do track surveys. We measured the positions of the cracks. We measured how long the surface length of the cracks were, how far they were away from the gauge corner, and how far they extended up onto the crown of the rail, the angle at which they're positioned on the head of the rail. We collected data about the track alignment and the track geometry. We knew exactly what the curvature was, the cross level, and how that varied at each bearer or each sleeper through the site. We measured rail profiles. We needed to actually understand the forces, so we needed to understand what the rail shape of the rail was. And we got vehicle dynamics models of the vehicles that were running over the site. We monitored the vehicles to see what sort of trains were running over the site. I spent ages pointing a radar gun at the backs of trains as they went past to work out what speed they were doing. Yeah, it's not a good idea to point a radar gun at the front of a train because you freak the driver out. But we did a lot pointing radar guns at the backs of trains to really understand what the speeds were, because that was the only way we could get the data that we needed. And then in collaboration with the train operators, we were able to go and measure the wheel profiles as well, so we could really get what was going on. And so we sort of employed all that data, stuck that into a vehicle dynamics simulation of all the different vehicles. So there were lots of simulations to do, one for each vehicle type, one for each wheel profile we did. Output was all the forces that we thought we might need to look at, and then we could test hypotheses of different fatigue models against what we actually saw on track. And this was really a giant step forward in actually being able to understand RCF. So it's about taking a small subset of data, but knowing absolutely everything there is to know about it. So we go back then and say, right, okay, we've got this data, we've got the simulations, we know how the forces vary. Let's put that into our classical rolling contact fatigue models. So this is using shakedown theory, the stuff that had been proved to work in the laboratory and theoretically was right. But when you put that out in the field, it doesn't give you a good prediction at all. The black boxes you can see, so each of you've got if you like, a plan view of the left rail and the right rail. The blue and the green coloured contours is where the model is predicting you should get RCF. And in the rail, there's little black boxes which show you where the cracks were actually seen, and they're also mapped out on the picture of the switch and crossing at the top left. So the model is picking up how the contact patch is moving over the rail, but in this case, this model is giving a very poor prediction of what's actually happening in reality. So we needed to go back, and we needed to then be able to generate a new hypothesis or test other damage models. And this is when we started to look at, and again, Steve mentioned it yesterday, a parameter that was referred to usually as T gamma, and it's basically the frictional energy which is being dissipated in the contact patch as a wheel rolls along the rail. So that energy is being dissipated in the rail, and it's going to be doing incremental fatigue damage to the material right at the surface of the rail. And you develop the model based on that, and suddenly you get the predictions in the bottom right-hand corner, and suddenly you're spot on, and you get very good predictions of where the RCF is going to be, even down to the severity of it as well. So this was an amazing step forward in actually our understanding of RCF, but it was achieved by looking in great detail at a small subset of data rather than the whole network. So then you can step back from that and say, how can we use this model? And you can start doing parameter studies and understanding what the influencing factors are for the things causing RCF. And one of the biggest thing that we found is that actually it's the vehicle design. So it's nothing to do with metallurgists, it's nothing to do with the materials that's causing the RCF. It's actually the design of the vehicle and the way that vehicle design had changed over the years, and an increase in the primary yaw stiffness, so the actual suspension design and the stiffness of the components within the bogey level. I think somebody's poster might have just fallen down. Yeah, so the suspension at the bogey level within the vehicle, how that had progressed over time had actually unknowingly increased the forces that we were imposing on the rail, which was actually causing the fatigue damage. There are other factors as well. Wheel and rail profiles themselves have an impact. The curve radius and the cam efficiency obviously also play a part, but that tends to be a lesser part than the actual vehicle design itself. But we were only able to determine these once we'd done all the detailed modelling to start with. It was also helpful to explain why on Southern route, particularly the southwestern part of Southern, they'd had a sudden, from 2005, they'd had an enormous increase in the number of defects that they were getting that needed immediate attention, and they were growing very fast. And on that particular route, they'd had a sudden change from old 1950s EMUs. The whole fleet had been replaced almost overnight by wonderful new Siemens trains, which we were able to show was actually quickly the cause of the increase in damage. But at the time, when this happens, as an infrastructure manager, you're going, well, what have we done differently? Is it the poor track maintenance engineer who suddenly isn't doing his job? Is he not managing the railway in the same way? But actually, it's nothing to do with the competence of the TME. It's just down to the traffic and how that. So it really sort of increased our understanding of the forces imposed between the wheel and the rail. And it's not the vertical forces, it's the tangential forces. So it's the actual forces in the plane of the rail which are steering the wheels around the track. And the stiffer you make the suspension, the bigger those forces have to be to actually guide the vehicle around the track. But the advantage again is that then when you've got that detailed knowledge, you can take a step back and you can look at the wider view and you can start simplifying it and working out what things you don't need anymore. So we generated something that was first known as the simplified model. And basically, we just looked at quasi-static behavior of the vehicle and said, can that tell us anything about what's going on? And we applied that to our big data set that we started with of the RCF database that big spreadsheet we had. And suddenly, this model could explain 80% of the RCF that we were getting on the whole of the network. And it told us exactly why we were getting it where we were. And that was amazing. But we were only able to do that after we'd stepped back from taking a detailed view of what was going on. Let's go back. A colleague of mine I did a lot of work with, he used to refer to this model as the Timex model. So if you remember, he used to say that the fully detailed thing was like telling the time with a Rolex, right? It was really accurate, it was spot on, but for everyday use, you wouldn't want to wear it. You just want to go out with your Timex because you didn't want to break it. But this was the Timex model. I didn't touch anything, promise.
Oh, God.
Talk amongst yourselves. It's still on this little screen.
It's not picking up this computer now.
Oh, here we go. Let's come back.
Turn it off now.
Yeah, thank you. Yeah, so actually there is a place for the Timex model. It's simplified, but it's good enough in a lot of cases. So that's then led us as an industry to be able to use that understanding and use that research to actually influence the industry and what we do. So the first thing we do is actually we make the factors which cause RCF a contribution to the track access charges that are paid by train operators. So every train operator has to pay an access charge if they want to operate a train on a piece of network. And we say, actually, if your vehicle's got a stiffer suspension, you need to pay more than one with a softer suspension because you're going to do more wear and tear on the network. It's a bit of an incentive there for people to buy vehicles with nicer suspensions. Doesn't always work, but you know, if you're a top and you've got a fleet of 50 10-car EMUs and you save yourself a few pence on each vehicle, you're saving yourself millions over a year in operating costs. May not be, it's not a big driver for people buying vehicles, but it is for people operating vehicles. We've also done quite a lot with new train designs. So actually we've been involved in writing train infrastructure interface specifications. So we're able to say to manufacturers, if you want to operate your train on our network, this is how it needs to behave. An example here is the Class 700. The requirement was quite a stiff requirement because we knew the vehicle had to go around some very tight radius curves. We put in some quite tight constraints, but Siemens were actually able to deliver a much improved bogie on the vehicles that were there previously. So you've got an inside frame bogie now, which makes the whole bogie lighter, which reduces the forces on the infrastructure. Less unsprung mass, softer yaw suspension, and it ticks all the boxes that we wanted. And the advantage is that once they've designed and built that, that then becomes the default offering for any other trains you buy. So that bogie then gets used in the 707 and the 717 fleets and starts to go everywhere. Similar story with the 345s on Crossrail, tight specification, but if you look at any, what was Bombardier is now Alstom train on a suburban network, you'll find they've got pretty much the same bogies. So that's a success of actually trying to turn research into something that we can actually influence in the train world better. We've also got developments like this, like the hydrodynamic bush here, which actually is a bush that's got a variable stiffness. So on straight track, at high speed, it gives you a very stiff characteristic, which helps to keep the ride good. But on tight radius curves, the characteristics of the bush become very soft, so it's got very nice curving performance with low forces. And again, that's now been rolled out on a number of fleets across the network. Understanding the contribution of the forces, the steering forces, and how they're influenced by the wheel and the rail profiles has allowed us to, first of all, improve the rail profile that we tell our grinders to implement. Whether they actually implement it, I'm not entirely sure because it's quite difficult to achieve. But certainly it means that there are new wheel profiles which are available for train operators, which maintain the curving performance that people want from the vehicle, but actually reduce the forces which are acting at the wheel and the rail. So one of the things we learned looking back at the history of this is actually solving one problem very often creates another problem. So going back to before RCF, one of the big drivers for the science and the development of the science of vehicle dynamics, or railway vehicle dynamics in particular, which is actually a relatively new science, was actually the number of derailments that we were getting in the 1960s. The graph down here is rather staggering in that from the mid to the late 1960s, there's an exponential growth of the number of derailments that we had per year. So there were over 400 derailments of freight trains alone in 1968. Okay? The science of vehicle dynamics allowed us to improve and better understand how vehicles were behaving, to design them better, to actually understand the mechanisms by which they derailed, better design, better resistance to derailment. And we're now at the stage where the number of derailments that we're getting is sort of in the handful a year, on running lines, that is. Still can't get away from people pulling hand points underneath trains in yards, depots and sidings. But on running lines, you know, we're operating a much safer railway, and that's a direct result of a lot of the understanding that we've had in railway vehicle dynamics. But that understanding allowed us to change vehicle design, which unknowingly increased the forces at the wheel-rail interface, which then led to the generation of RCF. So if we look at it, this graph interestingly shows how that primary yaw stiffness, so the actual bogie design, how suspension systems got stiffer over the years. So the year along the bottom there, each dot is the year of manufacture of a different type of train. And you can see from the 1960s through the 1970s, we have a steady increase in the amount of, the yaw stiffness, the manufacturer's tendency to have higher stiffness. We look at the years that we were active in doing rolling contact fatigue research and starting to influence the industry, and we suddenly find that beyond then, people are starting to acknowledge that, and your stiffness is starting to come back down again. So again, another big win for us. You compare that with the first graph that I showed, which shows the number of defects that we're getting per year, and you can see there's a direct correlation between the growth in that curve and the change we've got in your stiffness. We've also been able to influence those vehicles which have been modified with softer suspensions, with understanding what's going on. So benefits to the train operators in reducing truck access charge, less wear and tear to our infrastructure, making it more reliable. But my concern has been that some of the vehicles are starting to get stiff again. So people are starting to forget the lessons that have been learned. These are two fleets of vehicles, and in the last couple of years, I've been contacted by the operators of both these fleets of vehicles to say, we've got RCF on our wheels, can you help us? So that's really about RCF. This is about that simplified model, which is now implemented in a much more detailed way for our track engineers. So we've got a tool now referred to as TrackX, which allows track engineers to be able to assess where they're going to get rolling contact fatigue, but without having to do all the detailed vehicle dynamics simulation. I think my job is really to take a systems approach to track asset management. So we've done a lot of research looking at other forms of rail defects. So this is a form of rolling contact fatigue that occurs on the low rail of tight radius curves. Done a lot of research using the same sort of principles, but we can better understand what's causing this. Until we did that, track engineers really didn't know what was causing that. It doesn't look like it's rolling contact fatigue, but we can show that it's caused by the same forces. We can also apply those to do more fundamental research. So we can actually look at things like how vehicles respond to different wavelengths of features in the track. If you imagine say a lateral alignment feature in the track, when the vehicle sees that, it actually sees it as if it's going into a curve. So it'll start generating the forces that it would as it goes into a curve. Therefore, we're going to start to get damage and deterioration from those increased forces. And so we can do we've done some research to understand how vehicles respond to different track features. Interesting piece of work looking at thermography of the wheel rail interface. So this is all how we can use systems thinking and vehicle dynamics simulations to better understand what's happening at the wheel rail interface. So again, that frictional energy which is being dissipated at the wheel rail interface, that's going to cause some thermal changes in the head of the rail. So the question is that something we can measure? So we put a thermal camera on the train, you can measure it, and then we can also do some simulations to predict whether we're getting the temperature changes that we expect we are. It's one of those things that you do it, the simulation comes out and you go, that's really good. How can we use this? Not really sure, but it might be useful. We use it a lot for incident investigation, so derailment investigation. We do a lot of simulations to help understand what the mechanism of a derailment was or why a particular vehicle in the train had derailed. The 14th vehicle in a freight train derails. Okay, you might find a track defect, but you've got to ask yourself, well, why didn't it affect the first 13? So it's very useful for that. I refer to this as bringing some science to track engineering. I know we've got at least one track engineer in the room. And track engineering is very often seen as, or hit it and see what happens. It's quite basic, not a lot of science in it. This is a problem we had with lubrication, in that we had some greasers installed on the rail, but the trains weren't picking up very well and just spraying grease everywhere. So after the passage of the train, you would find that the little blobs of grease had not been picked up at all by the train and just splashed along the head of the rail. So some vehicle dynamics studies were actually able to show how the wheels actually moved as they approached that grease applicator and whether or not they could pick it up, with some recommendations about what we should do in the future. And then there's passenger ride. So we're getting further away from the wheel rail interface, but it's still important and it's still a factor from the wheel rail interface. So this is a design of a switch and crossing. It's installed and it's maintained to design, but people started to complain about poor ride over it. Track engineer goes out, does a track survey, says I can't find anything wrong with it, it looks fine to me. It's as it was designed and as it's installed, absolutely fine. Do the vehicle dynamics simulation, and you find that actually when the vehicle gets from the toe of the switch, that because of the design of the crossing, the vehicle actually gets a big kick, which actually turns itself into a jolt that the passengers feel and report bad comfort. So nothing wrong with the actual, well, there is stuff wrong with the design, but basically it's been built as it's designed. So it's not the track engineer's fault, but it basically means that you need to have a fundamental think about how you design S&C to actually overcome problems like this because of the poor ride you're getting. Another problem is adjustment switches. So where we've got expansion joints or adjustment switches, again, I was invited to investigate some problems that we had with batter and the damage on the head of the adjustment switch. And actually, when you look at the design of the switch, the changes in the rail profile that the manufacturer puts in, again, according to the drawing that they're supplied with to manufacture it, you find that it's not good for the passage of the contact patch. So the red lines on the top one there show where the contact patch is predicted to go as it runs through the switch. And actually, they actually take it to run on the very narrow part of the rail, on the tongue of the rail, rather than transfer the contact onto the much wider rail that it should be transitioning into. And that's just because of the manufacturer's drawing, which was put together without thinking about the vehicle dynamics. It was put together from a manufacturer's point of view for something that they could easily manufacture. And there was no consideration of how vehicles would actually behave and what would actually happen to the contact patch when it went overlap. So what are the future? So there's clearly lots of problems which are always coming out about vehicle track interaction issues. There's still lots to do. For me, the big thing is always the system thinking. Get away from the silo thinking. We've got new data streams that are becoming available now. So increased use of aerial surveys. So helicopter and drone surveys are becoming much more available now. They're very good at giving you a general overview of what's happening at a particular location. Can't give you the level of detail that you need from a track walk. Things like the eddy current data, I showed that graph earlier. We've clearly got problems with the distance alignment on it, but I think there's a lot that we can start to get from that data. There's automated visual inspection systems. These are some screenshots from a system known as AVA. So you can actually, so it's a set of cameras which are mounted underneath a vehicle. There's like half a dozen cameras underneath it, so you're getting views straight down on each of the rail heads. You're getting also angled views either side. You're getting forward and rear facing images, and the quality of the images is very good. And you can actually take select different runs at different times and see what's happening. And these images are good enough that we can actually pick out railhead defects like the two ringed there, which are actually rail squats. So they're another form of rolling contact fatigue defect. So whereas we used to either manually walk the track and look for these or rely on an ultrasonic system to try and pick up rail defects, you can pick them out visually using this system. And what's more, you can train an AI system to actually look for them yourself. And what we're starting to find is that the AI system finds a lot more squat defects than we find. It's a lot better. It doesn't get bored looking at pictures, but it sees a lot more than we do. And it flags them up, and you look at it closely and you go, oh yeah, there is actually a squat there. So we've actually starting to be able to get a lot of the data that we wanted when we did those detailed track surveys 20 years ago. We're sort of starting to be able to get a lot of that information now from doing surveys like this. I did a track walk 6 months or so ago, and before I went on site, I scrolled through this step by step to see exactly what I wanted to look at in more detail and what measurements I wanted to take, and it was really useful for when I got to site. Can't tell you anything about rail profiles, which we still needed to measure by hand. But yeah, you can actually see, so these are some of the side views from that system. You can even see where where flagged defects have been marked up by people writing defect numbers and things on the side of them. You can also see changes in running band, which are happening after you've got a poorly aligned weld. You can see on the rail there, head there, change in the running band. But at the moment, we still need to go and do those track site visits to be able to click the rail profile data that we need to be able to put into simulation. And as you can see, with access that's harder and harder to get, those site visits invariably can only be done at night time now. And I'm getting to an age where I don't like being up all night. So roll on improved data.
Sorry, Mark. In the interest of time, just
last slide.
okay.
You stop me. But we are getting to the point now where we have got automated systems that can pick up rail profiles from our ultrasonic test trains. We're doing assessments as to how good those profiles are, with what confidence can we use them in simulation. But we're getting there. So I am hopeful that we get all the data that we need without that track access. So what of the future? Yeah. So the challenges are that we're getting less access to track, which means two things. You get less access to track to do any maintenance or any correction. So we've got to do our bit to make vehicles and track more friendly to each other so that there's less need to go in and do maintenance. New rail materials. I haven't really talked about rail metallurgy. I sort of left that to Steve yesterday. But what can rail metallurgy do? Now that we understand what the forces are that are causing RCF and other defects, what can we do to actually use that to influence rail metallurgy to make the metallurgy more resistant without, which is the current approach, in that Steve sells us a new bit of rail. We say, how does it form? And he goes, oh, it's going to be really good, really good. But we don't really know until you put it in a piece of track and you monitor it for a year. And then you go, actually, it's not as good as all that, is it? Go back. So it's a bit of a suck it and see. We want to be able to turn that round to say, this is the metallurgy we want because we know it will have a better resistance. So that's what Phil's PhD is doing. So she's going to tell me to tell Steve what he needs to do, aren't you? Yeah. There's lots of other things. I've listed them there. If you're really interested, I've written a wheel rail interface strategy, which has been adopted by the industry and is available on the RSSB website. Go through, read it, give you some ideas and say, yeah, I'd like to do a research project in that, and then get in touch with us and we can hopefully put something together and get it done. Okay, that's me. Thank you. And sorry for going on.
Unfortunately, we don't have time for questions, but Mark is here for the
10 minutes.
well, you should be here for most of the rest of the day.
Yeah, I am.
So just moving things on, we've got the next presentation session, which is electrification, energy and decarbonisation, chaired by James Scott.
Okay, heads up on